Somewhere in our own galaxy, there's an object powerful enough to fling particles across space carrying more energy than anything humans have ever built. More than 100 times what the Large Hadron Collider can produce. And until very recently, we didn't just lack proof it existed. We didn't even know what kind of object to look for. Right now, as you watch this, invisible particles are slamming into Earth from every direction, hitting our atmosphere hard enough to trigger chain reactions capable of knocking out satellites. Physicists have chased the source of these particles for more than 100 years. For most of that time, the honest answer was, we have no idea. That's finally changing. And what one mountaintop observatory in China just found is more extreme than almost anyone expected. Subscribe now, because this field is moving fast, and there's a lot more still waiting to be found. Look up at the night sky and it feels calm, quiet, completely disconnected from anything happening down here on Earth. That impression is misleading. The story starts in 1912, when Austrian physicist Victor Hess made a dramatic hot air balloon ascent to roughly 5,300 meters, carrying instruments built to measure how quickly the air around him was becoming electrically charged, a process called ionization. At the time, most scientists expected ionization to drop the higher you went, since the assumed source of this radiation was the ground beneath your feet. Hess found the exact opposite. At high altitude, ionization levels were roughly 3 times higher than at sea level. That single unexpected result forced a huge realization. Whatever was causing this radiation wasn't coming from Earth at all. It was coming from space. Hess had discovered cosmic rays, and they've been hitting our planet nonstop ever since. Extremely high-energy particles, mostly protons, traveling close to the speed of light, slamming into our atmosphere and triggering a cascade of secondary particles that rain down toward the surface below. This isn't just an abstract curiosity. Those secondary particles, muons, neutrons, electrons, positrons, gamma rays, interact with living tissue and contribute to radiation exposure over time. When cosmic rays strike satellites or other electronics in orbit, they can trigger sudden bursts of ionization capable of degrading circuits or causing outright equipment failure. Our technology has been dealing with these particles for decades. Our scientists have struggled just as much to explain where they actually come from. For more than a century, pinning down the origin of cosmic rays remained one of the biggest unsolved puzzles in high-energy astrophysics, and their physical behavior makes them brutally hard to trace. Magnetic fields scattered across the galaxy bend their paths long before they ever reach us, and by the time they hit our atmosphere, they've already shattered into showers of secondary particles, destroying any direct clue about what they originally were or where they came from. That difficulty becomes obvious the moment scientists plot the cosmic ray energy spectrum, essentially a graph of how many particles at each energy level are arriving at Earth. That graph reveals something odd. A steep bend researchers call the knee. Beyond roughly 4 quadrillion electron volts of energy, cosmic rays become dramatically rarer. For years, some scientists guessed this bend might mark a dividing line between cosmic rays born inside our own Milky Way and ones arriving from far beyond it. Others simply weren't sure. And just as the field seemed ready to accept defeat on the question, one observatory changed everything. That observatory is called LHAASO, the Large High Altitude Air Shower Observatory, a ground-based facility sitting nearly 4,500 meters above sea level in the mountains of Sichuan Province, China. Its mission is simple to state and brutally difficult to achieve: find the highest energy particles anywhere in the universe. Pulling that off requires 2 things working together. First, the detector needs to be enormous, because the highest energy cosmic rays are extraordinarily rare. Fewer than 1 particle per square kilometer is expected to strike Earth in an entire century at the very top of the energy scale. To catch enough of these rare events to actually study them, LHAASO covers ground equivalent to roughly 190 football fields laid side by side. Second, once something is detected, researchers need to work out what the original particle actually was: a proton, a helium nucleus, or something heavier, based purely on the shower of secondary particles it leaves behind when it slams into the atmosphere. LHAASO tackles that reconstruction problem using at least 3 different interlinked types of detectors working together across its enormous array. The breakthrough came remarkably fast. Even while only about half the observatory had been built, researchers switched it on for roughly 6 months of test operation, and immediately started detecting far more high-energy gamma rays than anyone had anticipated. By 2021, LHAASO had recorded gamma-ray photons carrying more than 1 quadrillion electron volts of energy, including one photon reaching an astonishing 1.4 quadrillion electron volts. At the time, the single highest energy photon ever directly observed. For context, that's roughly 150 times more energy than the fastest protons ever produced inside the Large Hadron Collider, the most powerful particle accelerator humans have ever built. Here's where basic physics forces an important conclusion. Energy conservation tells us that particles carrying this much energy don't just appear out of nothing. Something out there had to actually transfer that colossal amount of energy to them. Scientists had theorized about this kind of source for decades without direct proof. LHAASO's discovery finally confirmed it. This class of extreme cosmic accelerator is now known as a PeVatron, any astronomical source powerful enough to accelerate particles up to peta-electronvolt energies, roughly 1 quadrillion electron volts. Confirming PeVatrons existed was one thing. Actually finding them was the next challenge. Fortunately, gamma rays carry a useful property that helps here. Because they have no electric charge, they travel in perfectly straight lines through space, completely unaffected by the magnetic fields that scramble the paths of charged particles like protons. That meant LHAASO could actually trace detected gamma rays back toward their general point of origin. By mapping these trace lines across the sky, researchers identified 12 distinct sources capable of producing these ultra-high energy gamma rays, several of which showed clear signs of accelerating particles all the way up to a full quadrillion electron volts. There was still a catch. Knowing the general direction a gamma ray came from isn't the same as knowing how far away its source actually is. 12 lines pointing endlessly out into deep space isn't exactly a narrow search area. Luckily, one more fact about these particular gamma rays helped tighten the search considerably. Ever since the Big Bang, the universe has been filled with a faint background of very low-energy photons left over from that early hot state. Ultra-high-energy gamma rays traveling through space are likely to collide with these background photons eventually, and when that collision happens, the gamma ray simply doesn't survive. That effectively puts a maximum travel distance on gamma rays at these extreme energies. They can't cross vast cosmic distances intact, which meant that if LHAASO was detecting them here on Earth at all, they couldn't have traveled very far to reach us. In fact, this ruled out the possibility that any of these 12 sources sat outside our own galaxy entirely. They had to be located somewhere inside the Milky Way. That single realization did 2 things at once. It proved the mysterious knee in the cosmic ray energy graph had nothing to do with particles arriving from beyond our galaxy, and it brought the search for these sources dramatically closer to home. The hunt was officially on. Before LHAASO's results came in, astrophysicists already had theories about which kinds of objects might reach these energy levels. Space is full of strange, extreme environments, but only a handful seemed capable of producing PV-scale particles. For roughly 70 years, one leading idea centered on supernova remnants, the expanding debris left behind after a massive star explodes. They certainly carry enough raw energy. Calculations suggest that if a supernova remnant converted just 10 to 20% of its kinetic energy into accelerating particles, it could account for most of the cosmic rays observed throughout our galaxy. When a star explodes, it drives material outward, creating a sharp shock wave where density, magnetic fields, and pressure all change abruptly. Particles that encounter this shock get repeatedly bounced back and forth across it, gaining a little more energy with each pass. A process called diffusive shock acceleration, sometimes called the Fermi mechanism. The catch: reaching truly extreme PV energies through this process appears possible only during roughly the first 100 years after a supernova explosion, and every supernova remnant we currently know of is far older than that. There's one possible workaround. If particles inside a young remnant escape its confining magnetic fields early enough, they might drift into nearby giant molecular clouds and continue producing PV-scale gamma rays there, even after the original remnant has aged past the point of accelerating particles that high on its own. Researchers believe up to 6 of LHAASO's original 12 candidate sources could plausibly be linked to supernova remnants. But they aren't actually the leading category scientists are most focused on. The next candidate reaches even more extreme energies: pulsars, rapidly rotating, extremely dense, highly magnetized neutron stars, the collapsed remnants left behind after certain supernova explosions. More than 1,500 pulsars have been cataloged so far. These objects are already known to accelerate electrons and positrons to extreme speeds, because their intense rotation and magnetism generate powerful electric fields strong enough to strip particles directly off the star's surface, creating a fast-moving outward wind of particles. When that wind eventually slams into surrounding gas, dust, or leftover supernova debris, it decelerates suddenly, forming what's called a termination shock, another site where particles can be driven to extreme energies. The third candidate came as something of a surprise. Looking closely at the shape of the cosmic ray energy graph near the knee, researchers noticed it wasn't a perfectly smooth curve. There was a subtle bump, an anomaly that didn't quite match what you'd expect from supernova remnants or pulsars alone. That mismatch forced scientists to consider more unconventional possibilities, eventually leading to what might be nature's most extreme particle accelerator of all, black holes. The idea that black holes could generate extremely high-energy particles actually goes back further than you'd expect. First proposed around 2009, describing a scenario where two particles falling toward a black hole collide right near its event horizon, potentially reaching almost unlimited energy in the process. For a long time, this was treated mostly as a curiosity, since any particles produced this way would presumably just fall straight into the black hole and be lost forever. That assumption changed with more recent modeling, which showed that a meaningful fraction of these particles would actually get ejected back out into space instead, escaping the black hole entirely and continuing onward through the universe as cosmic rays. So, having covered the theory, what has actually been confirmed? This search is genuinely difficult. Identifying 12 candidate regions in the sky is one thing. Pinning down the exact object responsible inside each region is a much harder, separate challenge. That search is still ongoing, but a handful of specific sources have already been confirmed. One of the first successes involves an object you may already recognize, the Crab Nebula, also known as Messier 1. The visible remnant of a supernova explosion sitting roughly 6,500 light-years away in the constellation Taurus. Beyond simply being visually striking, it's capable of accelerating electrons all the way up to a quadrillion electron volts. Because it's one of the most thoroughly studied objects in the entire sky, observing the Crab Nebula gives astronomers valuable insight into exactly how these natural accelerators operate. In gamma rays specifically, it shows dramatic variability, producing intense flares lasting anywhere from a few hours to a few days. Researchers now believe these flares represent bursts of serious electron acceleration happening in real time, though the exact mechanism, whether shock acceleration at the boundary of the particle, wind, or energy released when magnetic field lines snap and reconnect, is still debated. Remember that 1.4-quadrillion-electron-volt photon, the highest energy photon ever recorded at the time? Scientists were determined to trace exactly where it came from, and that search led them toward the Cygnus region of the sky. The constellation Cygnus is one of the most recognizable patterns in the northern night sky, spanning an enormous area. Inside it, researchers found something particularly compelling. LHAASO detected numerous extremely high-energy photons coming from what's been nicknamed the Cygnus cocoon, a massive bubble-shaped structure surrounding an especially active region of ongoing star formation. Inside that bubble sits a dense young star cluster called Cygnus OB2, an extremely energetic environment where large numbers of young, massive stars generate powerful stellar winds capable of accelerating particles. This cluster sits roughly 5,000 light-years from Earth, and its position lines up reasonably well with several of LHAASO's gamma-ray signals. But because gamma rays only point toward a general direction, not a precise distance, researchers often have to work through multiple candidates sitting along the same line of sight. And in the case of Cygnus, there were several other genuinely energetic objects worth considering. Roughly along the same direction as Cygnus OB2, but sitting much farther away, there's an object called Cygnus X3, an X-ray binary system made up of a massive donor star paired with a compact object, most likely either a black hole or a neutron star. The donor star is an extremely hot, massive type known as a Wolf-Rayet star, continuously feeding material toward its compact companion through powerful stellar winds. Combine that with the compact object's own tendency to blast out energetic jets of plasma, and you get essentially ideal conditions for particle acceleration. At first, it seemed nearly impossible to tell whether the extreme gamma-ray signal was coming from Cygnus OB2 or from Cygnus X3. But closer examination revealed something distinctive: a repeating pattern in the signal itself, cycling roughly every 4.8 hours, showing up consistently across gamma rays, X-rays, and infrared observations alike. Investigating further, researchers realized exactly what that timing represented. The compact object inside Cygnus X3 orbits its massive companion star once every 4.8 hours. That match confirmed the gamma rays really were coming from Cygnus X3 specifically, marking it as another confirmed PeVatron. Cygnus X3 turned out to be an especially compelling case. The highest energy photons detected from the system measured as high as 3.7 quadrillion electron volts. Since these photons are ultimately produced by even more energetic accelerated protons, that implies the underlying protons themselves carry energies of at least several tens of quadrillion electron volts. That places Cygnus X3 in an even more extreme category. Not just a PeVatron, but what researchers now call a super PeVatron. More recent analysis has gone further still, proposing that Cygnus X3 alone might power the entire extended gamma-ray structure of the Cygnus cocoon rather than the star cluster it sits near. Evidence that the accelerated protons inside this one tight binary system are escaping into the surrounding interstellar medium and lighting up a bubble of gas hundreds of light years across. That's a quick tour through some of the most remarkable PeVatrons discovered so far. But this search is still actively expanding. Identifying 12 candidate sources initially felt like an enormous achievement. Since then, that number has grown dramatically. In 2023, researchers published the first global catalog of confirmed galactic PeVatrons, listing 43 separate ultra-high energy gamma-ray sources. Continued monitoring from observatories worldwide has since pushed that total past 75 confirmed candidates. Finding more than 75 candidate PeVatrons scattered throughout our own galaxy genuinely forces a rethink of what the Milky Way is actually capable of. For a long time, many assumed our galaxy was a relatively calm, quiet place, since it lacks the supermassive black holes with violent, highly active pasts seen in some other galaxies. This research has thoroughly overturned that assumption, revealing a far more energetic, chaotic side to our own cosmic neighborhood than most people ever imagined. LHAASO isn't operating in isolation, either. It's actively collaborating with other high-energy gamma-ray observatories around the world, including facilities in the United States, Germany, Namibia, and Spain. That kind of international network lets different teams share data and cross-check each other's findings, building toward a far more complete picture of exactly how energy moves through our galaxy at the most extreme scales imaginable. It's worth understanding how an observatory like LHAASO actually manages to detect something as fleeting as a single high-energy particle, striking the atmosphere hundreds of kilometers away. When one of these ultra-high energy particles slams into the upper atmosphere, it doesn't simply stop. It triggers what's called an extensive air shower, a cascading spray of secondary particles that multiplies as it travels downward, eventually spreading out across an area on the ground that can stretch for hundreds of meters or more by the time it reaches detector level. That's precisely why an observatory chasing these events needs such an enormous physical footprint. A single detector in one spot would only catch a tiny fragment of the shower passing overhead. By spreading thousands of individual detector units across an area equivalent to nearly 190 football fields, researchers can capture the shower's full spread simultaneously, then work backward mathematically to reconstruct the direction, energy, and likely identity of whatever original particle triggered it. LHAASO combines several detection technologies to pull this off. Ground-based particle detectors track the spread and timing of the secondary particle shower as it reaches the surface. A separate array of water-based detectors, sensitive to a different type of radiation produced during these showers, helps distinguish between showers triggered by gamma rays and those triggered by charged cosmic ray particles like protons. An important distinction, since gamma rays are what let researchers trace a signal back to its source direction. On top of that, a set of wide-field air Cherenkov telescopes captures faint flashes of light produced high in the atmosphere as these particle showers develop, adding another layer of detail. Having multiple independent detection methods cross-checking each other is a big part of what makes LHAASO's identifications so much more reliable than earlier generations of cosmic ray observatories. It's worth putting the scale of these discoveries in perspective, too. Before LHAASO began publishing results, the entire field had only a small handful of confirmed ultra-high energy gamma ray sources gathered slowly over decades by observatories around the world. Within just its first year of partial operation, LHAASO alone had already matched or exceeded that entire historical total. Within a few years, that number climbed past 75. That kind of acceleration doesn't just add data points to a catalog, it fundamentally shifts how researchers think about the underlying population of these objects. Rather than treating PeVatrons as vanishingly rare exotic exceptions scattered thinly across the galaxy, the current data suggests they may be a genuinely common outcome wherever the right conditions exist. Massive young star clusters, energetic pulsars, or compact objects locked in tight orbits with a companion star. This matters beyond simply satisfying curiosity. Understanding exactly how and where the universe's highest energy particles get produced connects directly to some of the biggest open questions in physics as a whole, including how matter behaves under conditions far more extreme than anything achievable inside any particle accelerator built on Earth. Studying these natural accelerators gives physicists access to a laboratory operating at energy scales that will likely remain permanently out of reach for human-built technology, letting them test theoretical predictions about particle behavior under conditions that simply cannot be recreated anywhere else. What all of this research really shows is that our galaxy isn't the quiet, peaceful place it might appear to be from Earth. It's home to some of the most powerful natural particle accelerators known anywhere in the universe, environments reaching energies far beyond anything humans have managed to build with our best technology. We're still technically under constant bombardment from cosmic rays, exactly as we have been for as long as Earth has existed. But for the first time in over a century, we're finally starting to understand exactly where they're coming from. If discoveries like this fascinate you as much as they fascinate me, subscribe now, because this field is moving fast, and there's a lot more still waiting to be found.